Hello, everyone. So here we are, lecture number 4, the hidden lecture that we have here. We will be covering certain topics in your textbook that we still have not yet seen in the past 3 lectures. In particular, we'll be talking about functions, and specifically about functions, we'll be speaking about the linear function or the line. But before we do that, we're now going to give ourselves um, first of an introduction as to where are we going to be um, dealing with functions, like in what realm and what space. So the first thing to speak about is that our functions that we're going to be talking about, and you're going to hear the word functions a bit more nowadays, our functions are going to be particularly studied and looked at in what's called the Cartesian plane. So I believe many of you have heard about such a thing before. It's also known as the XY plane, the XY coordinate system. Many of these names mean the same thing. So the XY plane is also known as, so AKA the XY plane. And it's a plane, which means that it's two-dimensional. So we normally draw the axes. This is the x-axis, this is the y-axis. So the x-axis is our horizontal line that we draw first, and then our vertical line, we call it the y-axis. And the way this works is that at the center of these intersection, at the intersection of these two lines, we call this the origin. And the origin has every point in space in this Cartesian plane or in the XY plane, every point has an x and a y coordinate. So let me just say that every point in this plane has an x and y coordinate. So to define the middle points of this Cartesian plane, we call it the origin, and then the coordinates are 0, comma, 0. So one way to consider this plane is as if you had two number lines. You'll notice that when you draw this out, let me use a different color for this. When you draw this out like this, these tick marks, right? As you move to the right on the x-axis, you're going up on the positive side of the number line. And in this particular case, this is the x-axis. So the numbers move to the right, become more and more positive, and they become larger. Now, when you move to the left, and of course, this here would be 0. And as you move to the left, these are all the negative numbers, which makes sense if you consider this as a number line. So it's negative as you go to the left and positive as you move to the right. And then similarly, on the vertical axis, if you move upward, the numbers become larger and bigger, larger and more positive. And as you move on below it, each of these numbers become larger in terms of their distance to the 0, right? Their absolute value, but they're still negative in nature. So that's the way this is set up, right? And if I were to choose any point, and also before I do that, these, you can think of like these lines here dividing up a two-dimensional space into 4 equal spaces. So it moves into 4 different spaces. And the first upper right space, we call it quadrant 1. So this is quadrant 1. and then so on and so forth as we move and in the counterclockwise direction. We're going to call this quadrant 2. This is quadrant 3. And this is quadrant 4. So in quadrant 1, every point. So if I were to choose a point like this, like over here, this point right here, I move 7 units to the right, right? 1, 2, 3, 4, 5, 6, 7 units to the right, and I move 1, 2, 3, 3 units above. So this point has 7, 3. That's this point here in space. If I choose a point over here in the second quadrant, my x coordinate is negative, and my y coordinate in this case would be +5. So in the second quadrant, in the quadrant 2, or in the second quadrant, my x values are negative and my y values are positive. If I'm in the third quadrant, then if I choose a point such as the one over here, then this will be -4, -2. So both my x and my y coordinates are negative. And then lastly, if I move into the fourth quadrant, then I choose a point such as this one here, and this would be 5, -4. Okay, and in this case, in the fourth quadrant, my x coordinate is positive and my y coordinate is negative. So this is the XY plane. This is called the Cartesian plane. They also call it the rectangular coordinate system. So these are like several monikers that this has. So this is the rectangular coordinate system. It's a bit longer. And that also makes sense to call it rectangular coordinate, because if you choose a particular point, such as we did here, and we draw these little like dashed lines around, you see this gives it a rectangular feel. And normally you would see this in like grid lines here. And of course, there are squares. When you divide them up all evenly, like such as this, they become little square grid lines, but squares are rectangles. And the idea is that rectangles can be formed in this kind of grid. So that's why they call it rectangular coordinate system, the XY plane, or the Cartesian plane. And the Cartesian plane, this word Cartesian comes from the well-known, renowned mathematical thinker. He's more known as a philosopher, Rene Descartes. I'm not French, so I don't really know how to pronounce his name exactly as it should be, but he's well known for his phrase, "I think, therefore I am." So according to history, he's the person who actually had a dream, and he envisioned this kind of system where points can be placed in space and you have certain coordinates that are associated with that point. So that's the Cartesian plane. Now, we're going to be on this plane a lot, and in particular, we're going to discuss two formulas. So these are two formulas, two important formulas for Cartesian plane. Okay, so one of them is called the midpoint formula. And the second one is called the distance formula. So the midpoint formula is as follows. The midpoint formula is if you have 2 points, x1, so with 2 points, so I should say this, to find the midpoint between 2 points, x1, y1, and x2, y2, use the following formula. And the formula is x1 plus x2 divided by 2, comma, y1 plus y2 divided by 2. So that's the formula. And I'll give you an example to see how we use it. It's pretty straightforward formula. These coordinates here represent the averages of the x coordinates and the y coordinates. So I'll give you an example. So let's suppose I'm in the xy plane and I'm given 2 points. So let's see. If I choose the point 7 and call this 4. So if I have a point 7, comma 4 in space, and I have another point, let's say I have something like -6, comma 2, for example. Let's make this -5. So if it's -5, comma 2, and I have a point like this, what I want to figure out is what is that point in space on this in this Cartesian plane where it is equidistant. It is directly equidistant between, meaning it's the same distance to the both points. So one way to consider this is if you were to draw a straight line, I'm going to draw a dashed straight line. So if I drew a straight line through these 2 points, I want to know what point on that straight line connecting those 2 points, is it directly in between those 2 points that I originally marked out here? What would be that center point, that mid point? Where would it be? You would say it will be somewhere there, right? Where the X marked the spot. So because I have these points, I know the formula that could figure out, for which I can use to figure out the coordinates for the midpoint. So the midpoint formula states that I need to use x1 and then add it to x2. Now, what does that mean? That means that I can choose. For example, I can choose that x coordinate here. I can call this x1, namely, and then accordingly, I would call this y1. So this is like my first x coordinate and y coordinate. And then this one here would be x2, and this would be y2. So then now when I use the formula, x1 plus x2 over 2, comma y1 plus y2 over 2, then I know that I'm adding -5 plus 2, -5 plus 7 divided by 2, and then y1 would be 2 plus 4 divided by 2. So when I add -5 plus 7, I get 2 over 2, and when I add 2 plus 4, I get 6 over 2. But 2 over 2 is 1, and 6 over 2 is 3. So this here is my midpoint. This is my midpoint. See, these are the coordinates of midpoint. So then this coordinate right here, that would be 1, comma 3. So this point right here, 1, 3. So that point right at that moment, right at that position, is the distance between this point and the 7, comma 4 point, and this midpoint to -5, comma 2. Those two segments there, partitions, those two line segments are equal in length. So that's what the midpoint is. And I'm pretty sure maybe most of you, a majority of you, have seen this somewhere in your past math classes. So that's the formula. And now we'll talk about the distance formula. It's another important formula for the Cartesian plane. And I'll just give you the formula first. So let me give you some more background to this. So the distance formula is used to find the length of the line segment connecting two given points, x1, y1, and x2, y2. So we're going to be using this kind of formality of using x sub 1 or the subscript of 1, right? That number underneath the x in the lower right hand corner and in the lower right hand corner for y, those numbers indicate this is the first x, this is the first y, and then so on. This is the second x, this is the second y. So it's very much similar to the midpoint formula, but now the formula is a bit different. So I'm going to call d the distance, and the distance is given by this formula, the square root of x1 minus x2, square that, plus y1 minus y2, and you square that. And that's the formula. And let me just make a bit of a division here. So we're going to use the same example that we had here. So our 2 points are still going to be -5, 2. So we have an example here. We're going to continue it. We have -5, 2 on this point here, and we have 7, 4. And now my question is, find the distance between those 2 points. So I want to find how long is this? I want to find the length of this. If I were to draw, or if I were to measure this with a ruler from this point to this point, how long would it be? Or it doesn't have to be a ruler, any measuring instrument. How long would it be? And so then, because I have these 2 points, -5, 2, and 7, 4, right? I have 2 points. I can now call this, for example, I can call this x1, y1, and I can call this x2, y2. Now, it does not matter if I choose these to be x1, y1, or if I choose these to be x2, y2. I could have switched this around. I could have done the same. I could have just switched it. Now, what does matter is that if I call this x1, this has to be y1. It cannot be y2. I can't switch these subscripts around. I can't say this is x1, this is y2. I can't do that because then it just changes everything. Because now these numbers are not even, you're saying this is the first x and then this is the second y, but they're supposed to be paired up. These numbers here are paired. They're pairs. So you cannot say that these are different, come from different pairs. So you just have to be consistent with that. But beyond that, it doesn't matter which one is 1 and which one is 2, the first point or second point. So now I'm going to use the distance formula. So this is going to be the square root of x1 minus x2 according to the formula. So if that's the case, then I can do -5 minus 7, square it, plus, and then y1 is 2, minus 4, square that. Now -5 minus 7 is -12, and I square that. 2 minus 4 is -2, and I square that. Then when I square -12, I get 144. And when I square -2, I get 4. And then when I add them, I get 148. So the distance between the points -5, 2 and 7, 4 is exactly, now I think we can break this down a bit further. 148, I think I could divide 148 by 4, and if that's possible, this is 28, yeah, 37. If that's possible, then I can break this down. You know what? We're not up to that point yet. Let's just leave it like that. So it's exactly whatever square root of 148 is, units. Or we can say it's approximately. So approximately, if I take the square root of 148, it's 12.165. It's approximately 12.165 ... units apart. So when you put this in your calculator, you get 12.165. And these squiggly equal signs mean approximately. So when I write it like this is approximately. And of course, equal sign means exactly equal to. Okay, so the moment you put it in to the calculator and it spits you out a decimal, I know a lot of people are maybe comfortable with that. It's really an approximation. For the most part, when you have, for example, square root of 148, which is an irrational number, and irrational numbers have an infinite decimal expansion. And so when you put in your calculator of course cannot give you an infinite number of numbers since it's limited. And so it gives you an approximation. Okay, so that's how we use distance formula and midpoint formula. You can consider this under the category of what's called analytic geometry, because we're utilizing the concept of algebra with geometry principles. And what's interesting is really to understand why the formulas are what they are. So we're not going to go into detail as to why they are, but I would give you the opportunity to think about why is it that the midpoint formula is what it is the average of the x's and the average of the y's. To understand that, you would have to understand a bit more about geometry. And secondly, the distance formula, that's another formula that looks kind of convoluted. It looks like there's a lot going on, right? You're subtracting and you're squaring and you're adding and you're squaring and you're taking the square root. So it's like, wait a minute, why are we doing that? And if you study a bit more, what does distance mean in the Cartesian plane? What does it mean for two things to be apart? How do we measure that? You'll see that it really boils down to understanding the Pythagorean theorem. And that's pretty interesting how the Pythagorean theorem, something that was discovered thousands of years ago, is such a staple in understanding distance, particularly on the Cartesian plane. If we don't have the Pythagorean theorem, it would be very difficult to figure out how far away 2 points are in space without understanding a very basic understanding of finding the hypotenuse to a right triangle. So this, in a way, without divulging too much of the minor details, the distance formula essentially is the Pythagorean theorem. It's exactly the Pythagorean theorem. But okay, if you want to know more where that came from, you just ask me in my office hours or any other time through email. Okay, so there we are. We have these two major formulas that we discussed about the Cartesian plane. And now I would like to show you how to graph how to graph an equation with two variables. So a lot of times we're going to be dealing with equations that have two variables. In particular, one is the dependent variable and the other one is the independent variable. In other words, we have a y variable and an x variable. So for example, again, these are just examples. I want to graph y equals 3x plus 7. Some of you may notice what kind of graph this will end up being. But let's suppose we have no idea what the graph will look like, what we will see visually. So what we do is, and one thing I want to know is that x is considered the, it's like the input or the independent variable. And y is known as the output or the dependent variable. And what we do is we're going to use a table. So use a table of values. Now, which values are we going to use? That's really up to us. So here we are. So because I want to graph this on the XY plane, I'm going to draw the XY plane here, also known as the Cartesian plane. And I want to choose numbers for x's. So I want the x values to be around the region here. So if this is 0, right, this is 1, 2, 3, 4. So having numbers between maybe -3 and +3 for x values is a reasonable set of numbers. So I'm gonna start with -3 and then work my way up. So this is -3, -2, -1, 0, 1, 2, and 3. What I realized is that I should have, and I will make this a little bit bigger here. The y column, I'm going to make this a little bit more spread apart. And you'll see why. So we'll talk more about this in terms of what we're actually doing. So the x values are independent variables, meaning that they don't depend on anything, but the y values do depend. They depend on the x-axis, on the x coordinates. And so because of that, what the y value will be will depend upon what the x value is. So if the x value is -3, how do I figure out what my y value is? Well, what we do is we replace the x with the given number. So the y value associated with the x value is 3 times -3, which is -9 plus 7, which is -2. So my coordinates are going to be what? -3 comma -2. And then so on and so forth. Y will be 3 multiplied by -2 instead. Plus 7. This will be -6 plus 7, which equals +1. This will be equal what? -2 comma 1. And so on and so forth. Y equals 3 times -1 plus 7. This equals -3 plus 7, which equals 4. So this is -1 comma 4. And then y equals 3 times 0 plus 7. This is 0 plus 7, which equals 7. 0 comma 7. And then so on and so forth. 3 times 1 plus 7. This is equal to 3 plus 7, which equals 10. So this is 1 comma 10. Does everybody start to see what's happening? y equals 3 times 2 plus 7, which is 6 plus 7, which equals 13. So it's 2 comma 13. And then finally, y equals 3 times 3 plus 7, which is 9 plus 7, which equals 16. So this is 3 comma 13. Now, do you see how we're pairing these x, y values up and creating coordinates? And now what we're going to do, once we have the table of values, we're going to plot. So this is like our first step here. Our second step here is plot x, y coordinates from table of values onto the xy plane. So then step 3 would be to actually do it. So negative 3 comma 2, if I make these tick marks here, right? This is -1, -2, -3, and then I get -2. So this is 1, -2. This is going to be my first point here. This is going to be my first point. 3 comma -2. And then -2 comma 1. -2 comma 1 will be somewhere here. And then -1 comma 4, this would be 1, 2, 3, 4. This would be this point right here, -1 comma 4. And then 0 comma 7. This would be 4, 5, 6, 7. This is 7. And so on and so forth. As you go up 1, right? 1 comma 10, I'm going to be up even further up. Now we get the drift. We understand what's happening, right? We're moving up. If you see this, we're moving every point for the x values, we're moving 1 point to the right. All my x values are going up by 1. And then you notice that all my y values are going up by what? If you notice, -1, -2 to 1 is 3. 1 to 4 is 3. 4 to 7 is another 3 units that go up. 7 to 10 is another 3 units. 10 to 13, another 3 units. 13 to 16, another 3 units. So I'm moving my y coordinates 3 units up every single time I move 1 unit to the right for the x values. And because we understand this trend, we can already draw a straight line that is going to go through each of these points. And this straight line is the graph. So the straight line I should say this straight line is the graph of y equals 3x plus 7. And that's it. Of course, eventually, we're not going to be doing this same setup every single time. We're going to have a more streamlined way to graph, particularly something like this, which is called a linear function. These are lines. But the idea is that we can apply this method of table of values with any graph, with any equation of a graph, as long as we have the equation. We can plot x values, and then we can select x values, and then correspondingly, we can find the y values that are associated with that x value, create coordinates, plot those coordinates, draw a curve or a line that connects all those points together. And the more points you have, the more accurate your graph will look like. So that's the approach that we have for graphing. Okay. So using this table of values idea is very useful. It's very useful. Okay. So I've been using words that I haven't defined too clearly yet. For example, the word function. I haven't defined it. So let's define a function. So definition of function. And the keyword here is function. I forgot the article of A. So what is a function? A function, we're going to consider this as is a rule slash operation. In particular, our rule, quote unquote, will be a mathematical operation of some sort. That's why if you start to notice, hopefully, a lot of the things that we do, particularly in mathematics, is progressional, something that depends upon what we've learned before. So it's a progressional kind of subject. So if you don't know how to add, then you can't proceed to talk about multiplication and so on and so forth. So we need to develop a strong foundation to build upon previous knowledge. So it's a mathematical operation that does what? That assigns every input value. So this is a very particular way to describe our value. So it's an input value that is assigned to one and only one output value. That is a function. This is a just in words though. So one thing about studying mathematics is that to study something really well and to understand it really well, you have to approach it and view it from more than one perspective. So if I were to say in words what a function is, this is exactly what it would be. But of course, just having words and just hearing words is not enough. Sometimes having visual representations of things can give you much more insight than just me saying something, me just explaining it in words. So that this is how I would define a function. Now, what are other ways to describe it? We have other ways called the arrow diagram perspective, and also talk about what's called the machine diagram. So these are things, these are mechanisms to give you a better feel, intuitive feel for what a function is. I remember when I first learned about what a function was, I had no clue. Like I had no clue what really what anyone was talking about. And this is me back in 8th grade when I was first introduced to functions. It took me some time to understand it, but it's actually a fundamental concept, and particularly for those who are interested in computer science, for example, programming, this word function pops up all the time. You create a lot of functions when you program, but of course that's more on the computational programming side of things. But still, it's a fundamental uh, topic concept. So if you consider this as an arrow diagram, then the way we consider this is as an example. You can think of all the sets. We talked about sets, right? We talked about groups. So we can create like little groups and we're going to visualize them with circles. So the first group is going to be called the group of inputs or the set of inputs. And then the other one will be called the set of outputs. And of course, we can make these as with anything that we'd like. So for example, I'm going to make this very simple. And I'm going to say that my inputs have the numbers 1, 2, and 3. And the outputs have the numbers 4, 5, 6, for example. Okay, so we got 1, 2, 3 in the inputs, and then we got 4, 5, 6 in the outputs. And now what I'm going to do is I'm going to assign every input to only one output. It doesn't matter what the output is, as long as I only have one input assigned. For every input, I only have one output that's assigned to it, or connected to it, or attached to it, or corresponding to it, or associated with it. All these words pretty much mean the same thing. So if I do this, if I say 1 goes to 6, 2 goes to 4, and 3 goes to 5, what I just created, according to my definition, is a function. I have created a rule. What's the rule? The rule is this diagram, arrow diagram. So I've decided to say, hey, take 1 and the output of this would be 6, If I plug in 2 to this function, the output of it will be 4. And if I plug in the input of 3, the output will be 5. And this, I'm gonna call this is called f. F is a function. Done. That's the function. This is one way to look at it. Another way to look at it is if, like, I consider this as a conveyor belt, and this conveyor belt is going to a machine called F. And what F does is it does something to the input. So if I have my input and I call this X, and X is going through this in this direction to this function does something to X, and then what it produces outward, right? This is like one of those assembly line kind of visualizations. The output will be a corresponding Y. So if I use my example that I started with the arrow diagram, for example, if this was if my input was a 2, and I applied this function, this relationship, this correspondence to this input of 2, then according to this rule, I'm going to have the output of 4. So that's another way to consider the function. It's this arrow perspective diagram between 2 sets, inputs and outputs. And this machine diagram is another way to visualize or to have a clear understanding of what a function does. It's like a machine, it's like a black box where you plug in a value and you do things to it defined by the function, whatever that may be, and then whatever you produce, that will be your output. Okay, so those are just 2 ways to consider what a function is. And there's a third way, and it's called, we can consider it as a set of ordered pairs. So for example, I can call this a set, and I'm going to use the same example that I started with. And what would be the ordered pairs? And these ordered pairs are just x comma y, or in other words, input comma output. If my input is 1, my output is 6, according to this. So this would be 1 comma 6. The next coordinate, the next pair would be 2 comma 4, and then the next pair would be 3 comma 5. So this set right here is a function. Why is it a function? Because for every input, x value, quote unquote, my output is only 1. There's only one associated output to that input. Now, to understand what a function is, it's also useful to understand what it isn't. So these are examples, or this is an example of a non-function, I would say. Of something that's not a function. So I'll use the same arrow diagram here. Now what the problem will be, hopefully you'll see. This is 1, 2, 3, 4, 5, 6 again. And I'm gonna do one extra thing here that changes everything. So if I go 1 to 6, and if I go 2 to 4, and I go 3 to 5, but the moment I go 1 to 4 again, do you see how this is not a function? Is not a function. This is not a function. Why not? Well, the moment I took 1 and I have 2 outputs, I completely contradict the very definition of a function that assigns every input value to 1 and only 1 output value. And if I were to express this as a set of ordered pairs, then I would have 1 comma 6, 1 comma 4, 2 comma 4, and 3 comma 5. Now I'm just going to make this very clear. So the note is that the problem is not that the y values repeat. The problem is that the x values repeat. The inputs repeat. So a function, so this is note number 1. A function can have repeated y values. It can. It's okay. But note number 2, which is even probably more important than number 1, is that a function cannot have any repeated x value. The key word here is cannot. You cannot have any repeated x value. If you could express it as a set of ordered pairs, or if you have an input-output system here, you can't have repeated x values, because that would mean that the input has more than one output, because you're repeating the input value more than once. So I'm going to introduce a bit of more of terminology here. So equivalent term for input and equivalence terms for output. So for inputs, we're going to be calling them the x values. And for the outputs, we're going to call them the y values. They're also known as the independent variables. And the outputs are going to be associated with the dependent variable. And in particular, what's going to be more important than these terms is going to be what's called, for example, for inputs, it's going to be called a domain. So what's going to be the domain? It's going to be associated with the inputs, x value, and independent variable. And what's going to be the range? That's going to be associated with the outputs of the function. Okay, so this concludes part 1.